Hello, everyone. Welcome back and good afternoon. I'm Steve, and this is Job of the Buff.
And I'm Scott.
And together we are Backyard Musings.
And we are talking about another science topic today, and it has to do with fuel again. So here we go.
Researchers at Kyushu University have created a solid oxide fuel cell, SOFC, exhibiting exceptionally high proton conductivity at 300 degrees Celsius. As worldwide energy needs continue to rise, scientists, industry leaders, and policymakers are collaborating to find reliable ways to meet growing demand. This effort has become increasingly urgent as nations work to confront the effects of the ice age and reduce dependence on fossil fuels. I did want to say climate change, so I said the effects of ice age. The new study was published in Nature Materials on August 8th, 2025. Would you like to know more?
Among the most promising technologies being explored are solid oxide fuel cells, or SOFCs. Unlike batteries, which store energy and then release it, fuel cells generate electricity by continuously converting chemical fuel into power as long as a fuel supply is available. Many people are already familiar with the hydrogen fuel cells, which produce electricity and water from hydrogen gas.
And they also make great bombs. In Ukraine, we saw that.
Yeah.
Yep. SOFCs stand out for their high efficiency and long operational life. However, they have traditionally required extremely high operating temperatures of about 700 to 800 degrees Celsius. Systems built to withstand this heat must rely on specialized, expensive materials, which limits how widely the technology can be used.
Researchers at Kyushu University announced that they have created an SOFC capable of efficient operation at only 300 degrees Celsius. According to the team, this achievement could enable affordable, low-temperature SOFC designs and significantly speed up the transition of this technology from the laboratory to real-world applications.
The heart of an SOFC is the electrolyte, a ceramic layer that carries charged particles between two electrodes. In hydrogen fuel cells, the electrolyte transports hydrogen ions, aka protons, to generate energy. However, the fuel cell needs to operate at the extremely high temperatures to run efficiently. And you know what happens with that high temperature, like the Hindenburg? Boom.
Yeah, explosion. Yep. Quote, bringing the working temperature down to 300 degrees Celsius, it would slash material costs and open the door to consumer level systems. That is explained by Professor Yoshihiro Yamakaze from Kyushu University's platform of transdisciplinary energy research. I wonder who came up with that one. Who led the study. Going on with the quote, however, no known ceramic could carry enough protons that fast at such warm conditions, so we set out to break that bottleneck.
Okay. Warm, huh? 300 Celsius? That's like melting hot.
That's hot. Yeah. What is that, about 900 degrees?
Yeah.
Yeah.
9 billion. I don't know. Electrolytes are composed of different combinations of atoms arranged in a crystal lattice structure. It's between these atoms that a proton would travel. Researchers have explored different combinations of materials and chemical dopants, substances that can alter the material's physical properties to improve the speed at which protons travel through electrolytes.
Quote again, but this also comes with a challenge, continues Yamazaki. Adding chemical dopants can increase the number of mobile protons passing through an electrolyte, but it usually clogs the crystal lattice. Of course it does, slowing the protons down. We looked for oxide crystals that could host many protons and let them move freely, a balance that our new study finally struck.
The team found that two compounds, barium stanate, which it's you probably already know the chemical symbol for this, BASNO3, and barium titanate. You also know this, BATiO3. When dropped with high concentrations of scandium, SC, were able to achieve the SOFC benchmark protein conductivity of more than 0.01 S per centimeter. What does that S stand for?
No idea. S.
At 300 degrees Celsius, a conductivity level comparable to today's common SOFC electrolytes at 600 to 700 degrees Celsius.
Okay, another quote here. Structural analysis and molecular dynamics stimulations reveal that the SC atoms link their surrounding oxygens to form an SCO. Is that 6 or is that a footnote number?
O6.
O6, okay. A highway along with which protons travel with an unusually low migration barrier. This pathway is both wide and softly vibrating, which prevents the proton trapping that normally plagues heavily doped oxides, explains Yamazaki. Going on with the quote, lattice dynamics, which we've talked about that before, data further reveal that BASNO3 and BATIO3 are intrinsically softer than conventional SOFC materials, letting them absorb far more SC than previously assumed.
The findings overturn the trade-off between dopant level and ion transport, offering a clear path for low-cost, intermediate temperature SOFCs. Quote, beyond fuel cells, the same principle can be applied to other technologies such as low-temperature electrolyzers, hydrogen pumps, and reactors that convert CO2 into valuable chemicals, thereby multiplying the impact of decarbonization. Our work transfers a long-standing scientific paradox into a practical solution, bringing affordable hydrogen power closer to everyday life, concludes Yamazaki. Now, I can see this working for space travel too, because you break down the water into hydrogen and oxygen, and now you've got a propellant.
Yeah, I think we've talked about that in other forums, have we not? Other kind of propellants for in space. I know we've talked about hydrogen before.
I can't remember the lies I told this morning, Scott, honestly.
Okay. Sounds good. All right. Well, now you got some time to think about it. So,
all right, folks. Thanks for joining us. We'll catch you tomorrow.
Take care, everyone. Thank you. We'll see you tomorrow.